Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics. And we're in chapter 2, part of this playlist that I'm calling Discrete Random Variables. And let's jump to today's topic, which is expectation of discrete random variables. So in this section, we'll assume that we have a discrete random variable x with known density f. Let h of x be a function of a random variable x, which itself is a random variable, right? We don't know the values of h. It's assigned by chance because based on the random variable x. The goal of this section is find the mean value of h of x. So note that these expressions are all equal: mean value, average value, expected value, and we'll use them interchangeably. So the definition of expected value is let x be a discrete random variable with density f. Let h of x be a random variable. The expected value of h of x, denoted by e of h of x, is given by this. It's the product of h of x times f of x summed over all possible values. And it's provided that this sum, the absolute value of h of x, f, is finite. And that's just saying that it's not infinite. It's an actual number. Now, we're interested in special cases of h of x. So for example, h of x equal to x. So the expected value of x, denoted by mu, is, using the formula above, it's x times f of x summed over all possible values of x. And that's called the mean value of x, the expected value of x, denoted by mu. Another special case of h of x is x minus mu quantity squared. So the expected value of this, it's denoted by sigma squared, also called the variance of x, and it just called the variance. It's the x minus mu squared times f of x summed over all possible values. And if we think deeper about what we're doing here, is we're looking at the average squared distance from the mean. And so this is a measure of variability in our data. Another specific case of h of x is e to the tx, and it'll be denoted by m sub x, that's a subscript, of t. And it's called the moment generating function. This will be the whole topic of the next video. But it's the expected value of e to the tx is, e to the tx times f of x summed over all possible values. And it plays a major role in mathematical statistics. So we'll devote a whole video to that. Now, some rules for expectation. Let x and y be random variables and let c be any real number. The expected value of c is c. And if you think about that, what's the average value of c? Well, it can only be c, so it has to be c. The expected value of c times x is equal to c times expected value of x. The expected value of x plus y is equal to the expected value of x plus expected value of y. So expectation is a linear operator. Now, we'll prove number 3 and leave the remaining as homework. So the expected value of x plus y is x plus y times the density of x plus y. Remember, we have two random variables, and it's summed over all x and summed over all y. Now let's multiply this f of x into each of these and then split it on the plus sign there. So these two are equal, just multiplying that in. Well, when you sum over y, x is not involved, so we can take it out of that sum. And here, if we switch the order, sum of x first and then y, so we can take that y to the outside, and that's what we do here. Then when you sum over a variable of a joint density, it's like getting rid of it. It's what's called a marginal distribution after that. So this piece here is f of x, and this piece here is f of y. But that's the definition of expected value of x, and this is the definition of expected value of y. So the result follows. Now, computing the formula for the variance, sigma squared, it can be pretty tedious. So there's a shortcut formula for it. and it is this. So the sigma squared is the variance of x. Oh, and I'm missing a bracket here. So it's the expected value of x squared minus the mean squared, mu squared, which is the mean. And mu squared, of course, can be thought of as the expected value of x and the quantity squared. And again, I've left out a bracket there. So let's prove this. By definition, the variance of x is equal to the expected value of x minus mu quantity squared. It's the average squared distance from the mean. Well, this squared, let's just square that, the tuple there, or that equation. So you get x squared minus 2 mu times x plus mu squared. Well, expectation's a linear operator, so it goes into both of those. So it goes into the expected value of x squared. Oh, and this bracket should be in the front. So we get, right, when you take it in, you just get the expected value of x squared. And then you take it to this term, but 2 and mu are constant, so they come out of the expectation. And then mu squared is a constant, so it's just itself. So there should be a bracket right there, this bracket, okay? Well, the expected value of x squared comes down. Again, we're missing the bracket, but the expected value of x is mu. So you get minus 2 mu times mu plus mu squared. Well, that's mu squared. So it's minus 2 mu squared plus mu squared is minus mu squared. And that's what we get in the formula up here. And really, if you're going to calculate this by hand, this is the way to do it. Or often in theoretical derivations, this is the way to do it. And we're going to use this formula over and over and over. Now, the standard deviation is let x be a random variable with variance of x equal to sigma squared. Then the standard deviation of x is given by sigma, which is the square root of the variance. Now, the nice thing about sigma, or the standard deviation, the units of it are in the same units as your data. So there's you get a better feel of how spread out your data is by using sigma as opposed to sigma squared, right? The units of sigma squared are actually in squared units, which is often difficult to interpret sometimes. Theorem 3, the rules for covariance. Let x and y be independent random variables. Let c be any real number. The variance of a constant is 0, right? If it doesn't change, there's no variability, so it's 0. The variance of c times x is c squared times the variance of x. So when you're talking about variance, constants come out squared. Now the variance of x plus c is just the variance of x, okay? And the way you think about this, if you have your data, think of it as on a number line. And if you just move everything to the right by c, the variance of your data hasn't changed, right? You just moved it on the number line. And that's what this is telling us. Now, if x and y are independent, the variance of x plus the variance of y is equal to the sum of the variances, variance of x plus the variance of y. Now, we're going to prove number 2 and leave the others as exercises. So the variance of c times x is the expected value of cx minus c mu, but the c can be left factored out and then taken out of the squared, and you get this. Expected value of c squared is equal to your expected value of c squared times x minus mu squared. But since c squared is a constant, it can come out front. But then that just leaves the definition of the variance of x, and so the result follows. Now, we're going to end this by an R illustration, doing a real example here. Now, and essentially I'm using R because I don't want to type out all the numbers, but I think it'll help illustrate what's going on here. So we let x take on the values of 0 through 6. So we're a random variable that assumes the values, 7 values, 0 through 6. Now this density, it's called a binomial distribution. We're going to devote a whole video to it, but we're not going to cover it here. Just know that it assigns probabilities to the values 0 through 6. And that's what F is. So to find the mean, it's X times F summed over all possible values, and it's 3. The variance of X is you take X squared times F summed minus the mean, which is the sum of X times F quantity squared, which is 1.5. You could also use the more of the traditional definition of X minus the mean quantity squared times F summed over all possible values. And again, it's 1.5, as it better be. The standard deviation of X is you just take the square root of the variance that we calculated, up here, and it's 1.22. Now, if you were to do this by hand, you will need to create a table. And so what this table represents is how you would go about calculating the mean and the variance and the standard deviation. First of all, you need a row that is X, so 0, 1, 2, 3, 4, 5, and 6. Then you need a row that represents X squared. So you square each of the X's, 0, 1, 4, 9, 16, 25, 36. And then you need a probability density function. And we're using what's called the binomial. And again, we're not going to cover it. Just know that it assigns values, probabilities to these values. And so you need F, a row of F. Well, then you need X times F. So you take 0 times this value, 0. 1 times this value is this. 2 times you get 0.46. 3 times the F value. And then when you add those values, that's the mean. And then, of course, you need an X squared value too to calculate the variance. So the sum of these minus the mean squared is the variance. Now, we're going to test some expectation properties. So let's let C equal minus 3. And then the sum of C times F is minus 3. And that, oh yeah, because the expected value of itself is minus 3. So the expected value of X plus C, so let's create a variable Y, which is X plus C. And note that the sum of Y times F is equal to the sum of X times F plus C. Those are equal, so the property holds. If we look at the variance property, so we have C squared times the variance, that's what this is, and you get 13.5. But if we created a variable Y, which is C times X, and then created the variance of it, we get 3.5, which is the same. We have X plus C, assign that to Y, and then find the variance of Y. It's 1.5, which is the same as the variance of X. Okay, well, we're right at time. We need to stop. The next video will be moment generating functions. So I hope you enjoyed this one. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.